Well, it's a beautiful day to do some math, and let's work on some problems. And these problems are going to involve higher order derivatives, and we're dabbling in some applications as well. In fact, we're going to be doing a lot of applications in the next set of problems. And so let's do some problems. And remember that when you're doing these problems, you should do as much as you can on your own first. And make use of that pause button as you're going through and doing these problems. If you need help getting unstuck, go ahead, follow along until you get unstuck, and then pause and keep going, venturing out into the calculus wilds, exploring and developing your own set of skills. We want you to come out of this stronger and better, the great calculus champion. All right, let's begin. So, the position of a particle at a given time, where time is going to be positive, is given by the following. So S, remember S of t stands for position. It's 11 times the 4th root of t minus 3 times the 4th root of t to the 5th, e to the t. Wow, okay. Strange function, but okay. It is what it is. So there are some questions. When is the particle moving to the left? When is the particle moving to the right? And where will the particle be when it is at rest? So we need to remind ourselves. So what does it mean to be moving to the left? So when we're moving to the left, the position is decreasing. When we're moving to the right, the position is increasing. So my values are going in a positive direction. When we're not moving, well, position is neither increasing nor decreasing. So really what this question is asking in a very roundaboutish way is saying, well, look, left corresponds to where velocity is negative, right corresponds to where velocity is positive, and rest corresponds to when velocity is 0. So this is after understanding the velocity function. So we have position. If I want to start from position and I want to get to velocity, I'm going to take the derivative. So the velocity function is the derivative of position. And now we have to say, well, what's the derivative? So before we take that derivative, we should probably think about our function a little bit. So let's make sure we understand this notation. This is the 4th root t. See that little 4 there? That means I'm taking the 4th root. How do we write that in a more calculus way? Well, that would be written in the following. So it would be 11 t to the 1/4 minus 3. Now, this is the 4th root of t to the 5th, which is really the same as t to the 5/4. Now, it is the same, but writing as t raised to the power 5/4 in that format is a better way for us to write it because it helps us use our tools more conveniently. We're really set up to do like a variable to a number. That's our ideal writing. Okay, then there's this e to the t. Now notice this is going to be a product. And so when we start taking the derivative, we should have a product rule. So let's begin. That's a prime, by the way. It kind of looks like a very strange S. S prime equals, so the way I do the product rule, so I take the derivative of the first. So 11, derivative of t to the 1/4. The 1/4 comes down. Then it'll be t to the minus 3/4. And then minus 3. The 5/4 comes down. T to the 1/4. And then the e to the t. All right? Derivative of the first times the second. Plus the first, 11, t to the 1/4 minus 3, t to the 5/4, and e to the t. Okay, so there's our derivative in all of its splendor. Well, now we have to spend some time, and I think it's going to take some time. We really need to start understanding the sign. So we got to figure out a way to write this derivative in a more convenient way for us to work with. And when you're after understanding the sign of something, it's ideal if we can write it as a product of a bunch of pieces. Because if we have it in that format, then we can say, where do the pieces switch signs? So we're going to try to clean this up. In particular, we're going to try to really factor this out. All right. So how do we begin? Well, let's start by pulling out some common things. There's an e to the t in both. Okay, so let's just pull that out. And we'll keep pulling stuff out as we move along. So there's e to the t. And if I pull that out, let's see, we have an 11/4 t to the minus 3/4 minus 15/4 t to the 1/4. And here we have plus 11 t to the 1/4 and then minus 3 t to the 5/4. All right, next up, I want to keep pulling stuff out. Now, I see everything here has a power of t. So if I pull out a power of t, I should pull out the lowest power of t. So my options are negative 3/4, 1/4, 1/4, and 5/4. Actually, these will combine. So which one is the lowest? It's negative 3/4. So we're going to pull that out. Now there's one other thing I'm going to pull out. I'm going to do it right now. I asked, do they have anything in common? Well, no. 11, it's not a lot goes into 11. But I don't like fractions. Again, it's a personal weakness of mine, but I don't want them. So I'm going to pull out enough to get rid of all the fractions. So I'm going to pull out a fourth. So I'm going to pull out 1/4 t to the minus 3/4. And I still have that e to the t pulled out. And when I've done that, well, from the first term, I've gotten the fourth, the t to the minus 3/4, so I'll have an 11. From the second term, I've gotten the fourth. T to the 1/4, if I pull out t to the negative 3/4, will be what? It'll be t to the 1. You can think of it as 1/4, then I subtract, because I'm pulling out, negative 3/4, so that's 1/4 plus 3/4, which is 1. Now, how do we handle this one? Now you might say, well, wait a second, there's no 1/4, so how do we pull out a fourth? Well, one way to pull out a fourth is just to put a fourth in there. So you can imagine you have a little 4/4 action going on there. So that would, if you pull out a fourth, what would happen? Well, you'd end up with a 44. So plus 44. The other way to always check is to say, put it back in, and what do you get? Well, 44 times a fourth is 11. Similar process, we want to pull out negative 3/4 from 1/4. That would be t to the 1. Again, there's a check. Imagine putting that back in. T to the minus 3/4 times t to the 1 is t to the 1/4. All right, then minus, and then here we have a 3t to what power? Well, again, 5/4 subtract negative 3/4, excuse me, is going to be t, wow, what? T to the 8/4. That's t squared. All right. Good. So, hey, look at it. It's a quadratic. Nice. All right. So, what's next? Well, let's rewrite this quadratic. We'll combine the t's together. The other thing is, let's put the t squared in the front. And I'd like to have the t squared term have a positive thing. So I'm going to pull out a negative. So here we go. The last thing I'm going to pull out, negative 1/4 t to the minus 3/4 e to the t, the 3t squared. All right, minus 15 plus 44. Well, if you take 44 and subtract 15, that would give you 29. But because we pulled out the negative, it's going to be now minus 29 t squared, and then minus 11. Okay. Good. All right. I think we got everything. Oh, no, we messed something up. Do you see where I made my mistake? It's easy to make mistakes, so you always check your work. I didn't pull out the 1/4 properly here. See, there should be a 4/4 action going on here, which means that when I pull it out, this will actually not be 3, it'll be 12. So this is 12t squared. There we go. Now we're back. Good. Now we're cooking again. All right. You should always double check because it's easy to make mistakes. You see, I make mistakes. And I promise you, I probably have missed some mistakes that I've made, but I keep trying. And it's okay to recognize that mistakes happen. You keep checking your work and say, something doesn't feel right. Look for your mistakes. And if you can get to the point where you catch your own mistakes, you're in great shape. And it's okay to think about that. It's okay to say, hey, I was wrong. Let me fix it and move forward. All right, so we have all this stuff in the front. Now, we're going to cross our fingers and be like, I hope this factors. I really hope this factors. What do you think? Do you think it's going to factor this time? Boy, it would be amazing if it factors, doesn't it? Well, okay, spoiler alert, it factors. Now, this one is hard. I'll be honest with you. This one is tricky. So if you were to use the quadratic formula to find the roots, don't feel bad. No problems. But this problem has been set up so it factors nicely, so we actually can make progress. And so what do you know? Well, if we were going to do factoring, we would say, well, I have 11. There's not a lot of ways to break up 11, so it's an 11 and a 1. One of them will be a plus, one of them will be a minus. Now, 12, unfortunately, there are lots of ways to break up 12. But we have to think about it, because something's going to multiply by the 11. So I need 11 times something plus 1 times something to get to 29. So really I say, well, the 11 times something, that's going to be where I mostly end up. So I want 11 times something somewhere near 29. So if I think about the products that can go into, the divisors of 12, you get 1, 2, 3, 4, 6, or 12. If I were thinking about multiplying those by 11, there's 11, 22, 33, 44, 66, and among those, 33 is the closest. So I'm just will be a guess. All right, so maybe I put the 3 here, so 3t, which would make this a 4t. Now, would it work? Well, I'd have a 33t and a 4t. Hey, good news, 33 and 4 can get me to 29 when I subtract, and I do need to subtract because of the minus. Now I just have to pay attention to the signs. Well, should I put a minus here, or a plus, and a minus? Well, I want the minus attached to the 11 here because I want minus 33t plus 4t. Good. Now, here's our sort of moment of truth. Well, what do we know? We know a couple things. There's one thing that we said right at the very beginning of the problem that we haven't yet pointed to. Let's point to it. Time is positive. Now, let's think about our factors here. The minus here is definitely negative. What about this piece? The t to the 3/4 e to the t. What's going to be true about that? Well, the answer is it's always positive. Now, first off, e to anything doesn't matter. Any real number at all. Big positive number, big negative number, 0, it's always positive. Now, a positive number to an exponent is always positive as well. So this part is always positive. How about that 3t plus 1? Well, t is positive, so 3t plus 1, positive. All right. How about that 4t minus 11? Well, how about that 4t minus 11? What's going to happen? This is where things get interesting. The answer is it can change. So, what happens? Well, when does 4t minus 11 equal 0? Well, set 4t minus 11 equals 0. You'll end up with t equals 11 over 4. Now, you just start asking yourself the question, what happens to either side? So, if I'm below 11 over 4, so pick something smaller than 11 over 4. So like 1, that's like 4 over 4, that's smaller. 4 minus 11 is negative. So initially it's negative. After 11 over 4, pick something bigger than 11 over 4, like a million. Or you could pick 3. But they're both bigger, right? So you just have to pick something. So 3. 4 times 3 is 12, minus 11 is positive. So what happens is it's initially negative, and then it's positive. So I go from negative to positive. Now, we actually can write down our full answer. So there's a lot of things that we have to talk about in our answer. So let's start. When is the particle moving left? Left. Okay. That would be where we're negative. Now, if we're below 11 over 4, we'll have a negative, positive, negative, positive. We multiply it out. 2 negatives, 2 positives multiplied together. The result is positive. We're not moving left. At time 11 over 4, we're going to get negative, positive, 0, positive, which is 0. That's our rest. And after 11 over 4, negative, positive, positive, positive. So after that time 11 over 4, we are finally moving to the left. Okay, so we're moving left after 11 over 4. So moving left for t greater than 11 over 4. When is the particle moving to the right? Well, we've already figured that out. We actually know that. It's moving to the right below 11 over 4. So that's going to happen between 0 and 11 over 4. And the reason I have this, between 0 and 11 over 4 is because we know something that our time is positive. Now, the last question, and we got to be careful here because I noticed that I think I may have misread the original question. Notice how it's phrased. It's not a when, it's a where. So we figured out the when. The when is at 11 over 4. So the where, how do I do that? Well, the where would be at S of 11 over 4. That's where we're at rest. So that would be what? You plug 11 over 4 in. So that's 11 times the 4th root of 11 over 4 minus 3 times the 4th root of 11 over 4 to the 5th power times e to the 11 over 4. Right, good. And that finishes the 3 questions. When is it moving to the left? When is it moving to the right? And where, the location, is it at rest? Good. Nice. Nice warm-up, right? That was kind of long for a warm-up problem. That's all right. We'll have more problems. There's always more problems, right? There's always more problems. Okay. So, this kind of looks like a product rule question. But it says, hey, look at this. It's the second derivative. So we're taking the second derivative of f times g, and we want to express it in terms of f, f prime, f double prime, g prime, and g double prime. So we're sort of saying, hey, what happens to the second derivative for the product rule? All right, well, so how do we get to the second derivative? The answer is we take the derivative of the first derivative, the derivative of the derivative. All right, that seems reasonable. So the second derivative, which is this notation here, d squared dx squared of f of x times g of x, is the derivative of f of x g of x. So that's our situation here. So we're taking a derivative of a derivative, doubling down, two levels down. Okay, good. So we work our way inside out. So we can say, hey, I know how to take the derivative of f times g. So that's the derivative of, take the derivative of the first, f prime of x, g of x, plus the first, and times the derivative of the second. All right, good. Now, we come to our next step. We say, oh, it's the derivative of two things being added together. So what we can do is take the derivative of one and add it to the derivative of the other. So that is the derivative of f prime of x times g of x plus the derivative of f of x times g prime of x. Okay, well, now we have, we say, look what we have. We have a product and a product. and we're taking derivatives. So we use the product rule again. So what do we get? Well, the derivative of the first, the second derivative of x, times the second, leave that alone, plus the first, f prime of x, because that's the first, times the derivative of the second, which is g prime of x. Now we add to that, now we come to this one. The derivative of the first, that's f prime of x, times the second, you leave it alone, so the derivative of the first times the second, plus the first, f of x, times the derivative of the second, g double prime of x. Now you might notice that these two in the middle are actually the same. So we can put them together. So we end up with f double prime of x times g of x plus 2 times f prime of x times g prime of x plus f of x times g double prime of x. And there you go. That's the answer. Good. Now, before we leave this, let me just make a little observation here, because you might notice something. It's like, look at these coefficients, 1, 2, 1. They sound familiar. Have you ever seen those coefficients before? Well, I think you have, and they look like the following. If you look at a plus b squared, that would be a squared plus 2ab plus b squared. 1, 2, 1. Interesting. What do you think? Coincidence? So what if we think of a as saying, take a derivative of the f, and b as taking a derivative of the g? So it'd be like, okay, two derivatives of f, one derivative of f, one derivative of g, two derivatives of g. So let me ask you a question. It's true that a plus b cubed, if you work it out, that's a cubed plus 3a squared b plus 3ab squared plus b cubed. That's the, formula for a cube. So what do you think if I took the third derivative of f times g? What would it look like? What's your guess? And can you prove it? Can you run the computation? All right, that's just a fun aside. If you're looking for a fun challenge problem, and who doesn't like a fun challenge problem? We all like fun challenge problems. All right. So, let's see. Let's do another one. So, you're working on a machine that tracks mosquitoes and then shoots them with a high-powered laser. I like this machine. For the best effect, the mosquito should be shot while it has no vertical acceleration. So it can be moving up and down, but it's not speeding up or slowing down. It's the rate at which it's moving should be a constant rate. So that way the laser, it's a little bit better to aim. And it doesn't have to be going, it works better. Okay, all right, whatever reason, that's what we want. So given that for time between 0 and 7, the height of the mosquito is given by the equation h of t is 1/4 t to the 4th minus 4t cubed plus 45 halves t squared plus 50t plus 40 inches, where t is measured in minutes. Then determine the times that the machine would shoot at the mosquitoes. These are strange units, but we actually don't need to know the units, because first off, the question doesn't ask what the units are. What do we need to do? Well, we need to do what? We want the no vertical acceleration. Now, no is just another fancy way of saying zero. Zero acceleration. We have the height, and the height, that's vertical. Height means going up and down. So, if we want no vertical acceleration, that translates into saying we really want h double prime of t to be 0. All right, that seems reasonable. So let's get to h double prime of t. H of t, that's our 1/4 t to the 4th minus 4t cubed plus 45 halves t squared plus 50t plus 40. Now, h prime. Well, term by term. Derivative of 1/4 t to the 4th. 4 comes down, cancels with that 1/4, and we end up with t cubed. Derivative of 4t cubed, 3 comes down, minus 12t squared. 45 halves t squared, 2 comes down, 45t. Derivative of 50t is 50. And the derivative of 40 is 0. Goes away. It's a constant. Now, next round. H double prime of t. Okay. Derivative of t cubed, 3t squared. Derivative of minus 12t squared, minus 24t. Derivative of 45t plus 45. Derivative of 50, 0. It's constant. Goes away. Okay, good. So our goal is to figure out when does this equal 0. And it's pretty good for us. It's a quadratic. You're probably thinking, wow, every math problem is a quadratic. The thing is, right now, we don't have that many tools, and we're trying to do things where we don't have to appeal to a computer. So no, not every math problem is a quadratic, but it does turn out that quadratics are pretty useful. All right, so here we go. Let's figure out what we can do. Well, one thing, we can pull out a 3. So if we pull out a 3, we get 3 times t squared minus 8t plus 15 equals 0. All right, now, does this factor? All right, you're probably thinking, yeah, of course, everything factors. Well, okay, so that's 3. We need 2 things that multiply to 15 and add to 8. Well, that's actually pretty good, 3 and 5. So 3, and they're both negative because we want that minus 8t. So, again, that's equal to 0. So that leads us to 2 candidates, 3 or 5. Now, can we use either one? And you might say, well, yeah, those are when the acceleration equals 0, but be careful. Why do I say be careful? Let's go back to the problem. You see there's this constraint. Time has to go between 0 and 7. So the only times we can use have to be somewhere between 0 and 7. So if anything falls out of 0 and 7, we automatically throw it out. So we check, are these between 0 and 7? If either is, then that one works. If it's not, I'll throw that one out. So good news, 3 and 5 both are between 0 and 7, and therefore, yes, we actually get 2 chances to get that mosquito. Good. I feel like that doubles our odds. I like that. I like that. Okay, so there we go. And so we found our answer. All right, and remember, it's always good to check. Make sure that you answer it in the way that it asks you to answer it. So that's determine the times. Well, the times are time equals 3 or time equals 5. Good, so we did answer what was being asked for us. All right, good. On to the next one. All right. A projectile is fired into the air and lands in a valley. Its height in feet above the firing point is given by this formula, namely S of t is negative 16t squared plus 48t, where t is measured in seconds. So there's a question. What is the maximum height above the firing point reached by the projectile? Okay, and there's a second question. The projectile lands in the valley, 160 feet below the firing point. What is the speed of the projectile when it hits the valley floor? Okay, so how fast is it going at that moment? And notice it's asking for speed, not for velocity. So we'll talk about that difference in just a little bit. So let's think about the maximum height. So how do we figure that out? So if we think about what's happening is I have a position, and if I want to know the maximum height, so if we're firing something up, it's going to go up, and then it's going to go down. So our position at S, as it's going up, what's true about the velocity? So as I'm moving up, the velocity is positive because I'm increasing in height. As I move down, I'm decreasing in height. Velocity is negative. So where's that sweet spot where you peak out? The answer is where you have velocity equals 0. So I'm going to achieve maximum height at the moment when my velocity is 0. So here we go. So for part A, we have our great insight. Aha, our max height happens at time when our velocity, which is our s prime of t, equals 0. So let's see if we can figure out when that would be. So we take our derivative. So s prime of t is minus 32t plus 48. Set that equal to 0. Now we move a few things around. This is the same as saying 32t equals 48, or t equals 48 30-seconds. Now it turns out that 48 and 32 are both divisible by 16, so we can write that as 3 halves. So keep in mind this is our time, so this is 3 halves seconds. So 1.5 seconds after you fire it, so 1.5, it's at its peak. But what were we looking for? We weren't looking for a when, we were looking for a height. So what do we do with that information? Well, we now plug it into our function. Okay, so our height would be when we plug 3 halves in. So that's minus 16 times 3 halves squared plus 48 times 3 halves. Now, if you square 3 halves, that's 9/4. 16 divided by 4 is 4, and so you'll end up here with 4 times 9, which is a negative 36. Here, 48 divided by 2 is 24, times 3 is 72, so plus 72, which gets us up to 36. And our units here are feet. We can actually see it right there. Now, it doesn't ask for the units, but we're going to be polite and put units in just because we're good citizens. So we'll go along and throw some units in there. All right. Now there's a second part, part B. It's going to land in the valley 160 feet below the firing point. So what we should really think of is we have this projectile fired, and so there's something firing a projectile. Maybe it's like one of those little t-shirt cannons that they use to put cannons into a crowd at games. And so what happens? Well, we have our thing, it's being fired, and then it goes all the way down, and it lands down here. And something happens when it hits. There's an impact. Now, notice it's 160 feet below. Let's figure out how to translate that into a formula. So we want to figure out when it lands. See, if we know a time, then we're in good shape. Because if I have a time, I can plug it into the derivative. So I need to know a when in order to do that. So how do I do that? Well, I know where its position is at any given time, so I can ask, where is 160 feet below? Well, the answer is 160 feet below means negative 160. Negative because I'm down, I'm underneath. So when we're answering here for part B, we start by setting negative 16t squared plus 48t equal to negative 160. So we're trying to figure out at what time are we down so low. Now it looks a little bit messy. Let's move everything to one side. So let's move, let's say, these things across. So what would we have? We'd have 0 is equal to 16t squared minus 48t minus 160. All right, how do we handle that? Well, all these terms are divisible by 16. Certainly 16 is. 48, that's 3 times 16, and 160 is 10 times 16. So we divide by 16, you get t squared minus 3t, and then minus 10. So, fingers crossed, It's going to factor. And of course, surprise, surprise, it does. It's actually not a surprise that it does. So this factors as what? Okay, you're probably going to get pretty good at factoring. Two things multiplying together to negative 10, add to negative 3. That would be negative 5 and positive 2 do that. Okay, so what are our choices for time? Well, that leads us to two possibilities, 5 seconds or negative 2 seconds. I think we can rule one of these out. Just think of the problem. Because we like to think of time as moving forward. Time moves forward. And so negative 2 would be if somehow the projectile was being launched from 160 below, up through where we initially do it, and then keep going. So negative 2 is out. That's not what it is. So we've now figured out a when. When it hits the floor is at time equals 5. Next thing we have to figure out is the velocity. That comes from the derivative. So s prime of 5, and I have s prime, it's right here. That would be negative 32 times 5 plus 48. 32 times 5 is 160. So this is minus 160 plus 48. And if you put those together, well, minus 160 plus 48 would be minus 112. So that's the velocity. But remember, we mentioned it wasn't asking for velocity, it was asking for speed. What's the difference between velocity and speed? Well, it's about the sign. Velocity, you keep track of the sign. So the negative 112 says we're coming down. It's coming down. So the speed says, I don't care if it's coming down or going up. Get rid of the sign. I just need to know its size. So our answer is the speed is 112. And we can actually say what the units are because we know our units here, our feet are our distance, our time is seconds, and therefore it's 112 feet per second. And that's our answer for part B. All right, good, good, making progress. All right. Well, now on to what looks like a very long essay problem. Okay, don't be intimidated by very long problems. Usually what happens when you see a long problem is it means there's a short solution. But what they're trying to do is they're trying to hide an important detail somewhere inside. So let's not miss anything. All right, you've recently taken up a job on Moon 13 where you maintain and operate a machine that takes as input material blargs. Now you might be thinking, I don't know what a blarg is. You don't need to know. It's just something. Okay, and it will produce as output material furbles. All right, now you're like, now I really don't know. It's okay. Don't worry about what a furble is. It's not important. We can still make progress. And okay, where are we? This particular machine will take B blargs and produce f of b equals e to the 2b minus 36 e to the b plus 8b plus pi cubed furbles. Good. Whew. Now, our input, this is important. Let's just pause. Our input are blargs, our output is furbles. We can see this because b is a blarg, and it says here where our units are furbles in the output. And b is our variable. B doesn't sound like a variable name, but that's okay. We can use variable names to be whatever they want. They don't always have to sound like variable names to be used as a variable name. All right, we keep reading. You are trying to determine the current amount of input B being fed into the machine. So you refer to a monitor, which usually displays information about the value of the blargs, the value of the furbles, as well as rates coming from the derivative, the second derivative, the third derivative, and so on. Each readout including appropriate units. So notice how they emphasize this. That says, hey, units are going to be important here. Okay, we've got that in our minds now. You discover that the monitor is mostly broken. Well, that sounds right for Moon 13. The only thing which you can read currently states 88 furbles per blarg squared. Use this information to determine the current amount of blargs being fed into the machine and write your answer in the provided box. Oh, whoops, sorry. That part should not have been there. There wasn't a provided box. We took that box out. All right, well, here, we'll go. I'll put a box in. Here's our provided box. So we're going to write our answer in there. We don't know what it is yet, but we're going to find it. Okay, so what do we do? And can we achieve this? Oh, this is good stuff to think about. This is great stuff to think about. Okay, so let's pay attention to the units here. What do we see? Furbles over Blarg squared. So if we look at what this is, we see the numerator. This is our units of the output, what comes out of the machine. Well, that makes sense. We always see the units of the output in any derivative. The denominator is the units of the input, but not just units of the input, it's units of the input squared. If we think only about units, what is that telling us about what information we're seeing? This piece right here says this is a second derivative. So what we are told is that there's a second derivative on the display. The units are telling us the second derivative. This question is about, can you interpret units? Now, one of the things that makes this challenging is we have these weird words. Furble, Blargs. These are distraction words. We're not going to be distracted. We just know that these are words. It doesn't matter what words are used. The processes are the same. All right, so what's happening here? We now know that the output on the monitor is a second derivative reading. So what we can now say is, aha, we have been given that the second derivative with respect to b equals 88. That's what we now know. And what do we want? Well, we want to find b. Find our b. Okay, so now we proceed. So we start with our f. We want to get to f double prime. Two derivatives to go. So our f of b is e to the 2b minus 36 e to the b plus 8b plus pi cubed. So f prime of b. Now e to the 2b, we've actually done this one in an earlier practice in a previous session. Do you remember? Did you do it? You should have done the practice. Come on, keep doing it, keep doing it. It is derivative e to the 2b, the 2 comes down, 2e to the 2b. The derivative of e to the b is e to the b. Remember, b is our variable. And if it's throwing you off, think about, well, if it was e to the x and I took the derivative with respect to x, what would happen? It's the same thing, just with a slightly different name. And names shouldn't change how we do things. Derivative of 8 times b is 8. Derivative of pi cubed, oh, this is a red herring. They're trying to trip us up. Oh, they do this all the time. But pi cubed, what do we know about pi cubed? Because we're not going to be caught in their snare. It's a constant. It doesn't change. So the derivative of pi cubed is 0. Goes away. Nice. Now, second derivative, f double prime of b. Well, the 2 comes down again. So we get 4 e to the 2b. The next, minus 36 e to the b. Derivative of 8, 0. Gone. It's not there. All right, and now we said, well, what do we need to do? We need to set this is our second derivative, equal to 88. Okay, well, let's bring the 88 across. So, in the meantime, notice how everything is divisible by 4. So we get e to the 2b, because I'm going to divide by 4, minus 9e to the b, because I'm going to divide by 4. And when I divide 88 by 4, that's 22. Bring it across. That's going to be minus 22 equals 0. Now you're probably thinking, is this another quadratic? And it is! It's another quadratic! Wow! What are the odds? Actually, they're pretty good. We like quadratics. Now, how is it a quadratic? Well, e to the 2b is really e to the b squared. So this is a common trick. E to the 2 times b, e to the b squared, minus 9e to the b minus 22 equals 0. So we now factor. And what do we end up with? Well, what do we want? Well, see, the e to the b, that's like what we're factoring, right? So it's e to the b, e to the b. And then we want two things that multiply to 22. One of them is positive, one of them is negative. And combine together when we add to get to negative 9. So minus 11 plus 2. All right, almost there. So there's two possibilities. E to the b is negative 2. E to the b is 11. Now, one of these is right out. Can't possibly be true. Which one is just gone? Don't even have to think about it. Well, the negative 2, not even a possibility. Not going to happen. Why? Because e to anything is positive, no matter what you plug in. So I can't get e to something be a negative number. So it's got to be that e to the b is 11. Now, well, remember, what do we need? We need to find b. So if e to the b is 11, what is b? I got to get the b out of the exponent. How do we free the b? How do we pull it down? Well, we need to undo the exponential, which means we need a logarithm. So that's how we get things out of the exponent. So take the log of both sides, and we get b equals the natural log of 11. So our final answer, and I said we put it in a box, log of 11 what? Blargs. Okay, that's how many blargs we need. Log 11 of them. Oh, whatever that means. Well, it just means that's what there is. Okay, good. All right. Well, let's try one more. One more problem. Okay, so a particle's position on a line is given by a function. This function, t to the d minus 11t cubed plus 27t squared, where d is a positive number, and it's some parameter. We don't know what it is yet, but we're going to figure it out. Okay, now at time 1, the acceleration of the particle is 0. That's just a fact we're given. Determine another time when the acceleration of the particle is 0, and also determine all times t when the particle is at rest. So, we know at time 1 the particle is 0. At time 1 the acceleration is 0. So acceleration is s double prime at time 1, means plug in 1, is 0 equals 0. So what do? We start with s, and we start taking some derivatives. T to the d minus 11t cubed plus 27t squared. So s prime of t would be d, t to the power d minus 1. I don't know what d is, but the rule always applies. Follow the rule. Then minus 33t squared, 3 comes down, and then plus 54t. Then s double prime of t, because we want the acceleration. So here, d minus 1, that comes down. So d times d minus 1, t to the power d minus 2, minus 66t, and then plus 54. So there's our acceleration. We now have our acceleration. And what do? Plug in the 1. All right, so s double prime of 1 would be d times d minus 1. And the nice thing about 1 is 1 to any power is 1. All right. So d times d minus 1 minus 66 plus 54. Okay, that has to equal 0. So we get that this is d squared minus d, negative 66 plus 54. What do we know? Negative 6 plus 54 is negative 12. All right? So d squared minus d minus 12 equals 0. All right. Well, we're almost there. That factors. D minus 4, D plus 3 equals 0, which tells us two possibilities. D is 4 or D is negative 3. But wait a second. Oh, wait a second. We can knock one of those two out because we were told D has to be positive. That means the negative 3 is out. Can't happen. Can't do it. Can't do it. So D is not negative 3. So we've now found what D is. See, the D was some parameter to be chosen. We now know that D equals 4. So we can now answer our various questions. So what do we have? All right. It says determine another time when the acceleration is 0. So if we want to know when the acceleration is 0, we look at the second derivative, s double prime of t. D is 4, so it's 4 times 3, which is 12. Then it's t to the power 4 minus 2, which is t squared, minus 66t plus 54. Now, we can clean this up because everything here is divisible by 6. Everything's divisible by 6. So pull out a 6. That would be 2t squared minus 11t plus 9. And now we're like, well, we need to factor. Oh, wait a second. Factoring is going to be easy because, oh, this is cool. Remember what we said? We started with the s double prime of 1 equals 0. That means that 1 is a root. If 1 is a root, that means that when this factors, there has to be some piece where when we plug in 1, we get 0. So that means t minus 1 has to be one of our factors. Now the other factor, well, I need to have t times something produce 2t squared, so that should be a 2t. Negative 1 times something to produce 9, that has to be minus 9. And you can check, 2t squared minus 9t minus 2t is minus 11t, minus 1 times minus 9 is plus 9. Woohoo! We're doing it. We're doing it. So, if we want to set this equal to 0, that says our other time would come from when 2t minus 9 is 0. Well, that says 2t equals 9, or at time t equals 9 over 2. So that's our question to when is the acceleration of the particle 0. Now, if we want to do when is the particle at rest? Okay, so particle at rest means what? So let's just recall this is acceleration is 0. So particle at rest means what? Means that s prime of t equals 0. And remember, we want to find all the times t. So we're going to take our s prime of t, and let's see what that becomes. So that's s prime of t. We now know that d is 4, so that would be 4 times t cubed minus 33t squared plus 54t. Well, not a lot of common factors here. So, well, there is a t in common, so let's go ahead and pull that out. So that's t times, we get 4t squared minus 33t plus 54. Well, we had a good run, right? We were so close where we were like, wow, everything factors. Isn't it wonderful? I don't know. What do you think? Is this going to factor? Honestly, I think it should because I like things that factor, but we have to think about it for a second. I mean, what can we do? Well, because what can we say about t? Let's switch colors for a second while we think about things. So here we get the 1 or 4 combination, and here we get a 2 combination. Now 54, well, there's 1 in 54, but that's just way too big because that would be at least a 54 involved. A 2 and a 27, well, we got to get to size 33. So let's see, could we make it? Well, that's 27, and that would be 8. That would get us to 35, which is close, but that's not 33. All right, how about 3 and 18? Well, let's see. 18 and 12. No, that's not good. 6 and 36. No, that's not good. Okay, what else can we do? 54. 54. No, that's not divisible by 4. It is divisible by 6 and 9. Can we make that one work? Oh, wait a second. I think this looks. Look, you get 9 times 1, and that's 9. 6 times 4 is 24, and 9 and 24 do make 33. Okay, all right. So we're almost there. So we have t, and what did we say? We wanted 4 and the 6 to multiply. So that says 4t, 1t, 4 and 6 to multiply. So put a 6 here, a 9 there, and they're both negative because that's a positive 54, but we end up with a negative 33. Now, you should be nervous. It's a perfectly natural reaction. Let's actually check. 4t squared, check. Minus 24t minus 9t, good. And then plus 54. All right. So that's the first derivative. And now we say, well, when does this equal 0? Well, now we can list it, each individual piece. There's at time equals 0. Then there's at when 4t minus 9 equals 0, which would be 9 over 4. And when t minus 6 equals 0, which would be at 6. 0, 9/4, and 6. Wow, good. We actually found the answer. We shouldn't be surprised. Come on, we worked hard for these answers. We work hard for all our answers. But you know, the harder you work, the better it feels when you get it. All right, well, thanks for sticking in there till the end, and let's keep working on these calculus problems.